the topic is bending. The bending is related to if you hang on a beam, then you will put stress inside the bar you are hanging on. So, lady, which point do you think is the most dangerous point for the bar to break?
Middle.
Okay, someone said middle. Do you agree with him? Okay. How about you? If the bar is going to break, which point do you think is going to break?
The middle.
The middle? Okay. Most of people support the answer, but how about you? Your intuition. What will your intuition tell you? Which point is going to break?
I think the same, in the middle.
Okay.
There's no support here.
Okay. So that's why you come to the class. Because you got the wrong answer. Next page, please. Let's discuss something, some theory, before we jump into our answer. Like, on your right hand side, you'll see, suppose it's a rubber. The eraser, you used the eraser to erase the print of the pencil. Okay, so do you know the eraser? Okay, so eraser is going to be stretched out like the second figure. So you see, if we draw some tiny vertical lines on the eraser, if you stretch the eraser, you will see the gap between the lines becomes larger. Is that right? Do you agree? If you have an eraser, if you stretch the eraser, the gap between the lines you drew on the eraser is going to become larger. Okay? So if we cut the eraser into two sections, suppose at the cross section, you can draw some lines to represent the stress applied to the cross section, the force applied to the cross section. So if you apply two force, P at the right and P at the left, if you cross the bar, if you cut the bar, the left-hand side, you apply P, but there must be a force to balance the force P to reach force equilibrium. Otherwise, we cannot say the bar is going to keep moving to the left, but because we apply two force, one at the left, one at the right, it's going to be in equilibrium. It's going to stay there. So there must be a force. If you cut the cross section, there must be a force at the cross section to balance the force P. But no matter what, we define something called stress. Stress equal to force divided by the cross-sectional area. So we give the stress a symbol, sigma. So you just look at the final equation on your left. Sigma equal to force divided by cross-sectional area. So that's what you can take away from this PPT. Okay, next page, please. So now, like in the figure, we have a car hanging on a rope. So if the weight of the car is 600 pounds, then there are two forces applied to the car. One is the gravity, which is the weight W. The other force is the rope applied to the car. Because it's in equilibrium, so the force F must be the same as the weight W, 600 pounds. Then we can calculate the stress inside the rope. The stress is F divided by A. And the rope is a cylinder. So we can use the equation pi d squared divided by 4 to calculate the area of the cylinder. Do you agree? Okay. So if force 600 pounds and the diameter of the rope 0.1875 inch, then we can calculate the stress equal to 21,730 pounds per square inch. Pounds per square inch is PSI. Pounds per square inch, PSI. So can you repeat after me? Pounds per square inch.
Pound per square inch.
So the abbreviation is PSI.
Yes, sir.
Yes, okay. Okay, next page, please. So now, do some math, please, for this quiz. So, yeah, just get your hand on your calculator or your cell phone or anything you can use to calculate the stress in the rope. Force divided by the cross-sectional area is the stress. So, what's your answer? Yes, what's your answer? So, do you have calculator on your cell phone?
Yes.
Yeah.
But I forgot the function, how to calculate.
Oh, please go to the previous page. Previous page. PPT main, please. Yes. Yeah, this is the equation. Force divided by cross-sectional area is the stress. Okay, what's your answer?
101.862 KSI.
Okay. Okay, next page, please. Next page. Now, another quantity I would introduce is the strain. Strain is the deformation. Again, we have a rubber band. And we draw, okay, please.
Sorry.
We draw a square on the rubber band. So if you stretch the rubber again, so the deformation shape is the figure below. So what happened to the square ABCD? What happened to the square ABCD? ABC? So after you stretch the rubber, the square becomes A star, B star, C star. So what's the difference between A star, B star, C star?
Extended.
Yes. So extension and the distance between A, B, see the length A, B and length A star, B star. So which one is larger?
The L star.
I mean, you have square ABC, but after you apply force to stretch the rubber, Now, the original ABC becomes A star, B star, C star. So apparently, B star, C star, the length should be larger than the length BC. That's right. But how about the length A star, B star, and the length AB? Which one would be larger?
BC. This one. This one doesn't change.
C. Young man, could you be my model? Okay, please. Okay, yeah, raise your hand. So, if I stretch his hand, if I stretch his hand, AI guys, if I stretch his hand, the length of his hand is going to be longer. But what happened to the diameter of his length? If I stretch his hand, what will happen to the diameter of his hand? Yes, shorter, right? Thank you.
Okay.
So that's why A star, B star should be shorter than AB. But we want to define the strength. The definition is the change in length divided by the original length, epsilon. So what's the definition of the strength, young lady? Definition of the strength. Yes. Yeah, change in the length divided by the original length. So for this rubber band, the strain in the length direction is B star C star minus BC divided by BC. And the strain in the width direction is A star B star minus AB divided by AB. Okay? So that's the strain definition. Because in the study of the material, it's important for engineer to understand these two concepts. And so what's your major, please?
Horticulture.
Foreign language?
Horticulture.
Horticulture, like to plant, for the plants and to flower, arrange. Or horticultural therapy, like for elders to do the gardening. And we can use horticulture to help them to still stay active and young. Okay, so horticulture is okay. So for if your major is not engineering, it's not mechanics, maybe you won't be able to get involved in this stress strain. But it won't hurt to know this before the Christmas of this year. Christmas is close. Okay, strain. We have positive strain and negative strain. Because B star C star is greater than BC, so B star C star minus BC is it positive or negative? Lady.
Positive?
Yes, positive because B star C star is greater than BC. So for the strain in the length direction is a positive quantity. Now, how about if we A star B star minus AB, is it positive or negative?
Negative.
Yes. So the strain in the width direction is going to be a negative quantity. So extension, positive strain. Compression, negative strain. If we squeeze something, we are going to decrease its length. Okay, very good. Next page, please. thermal strength. Like usually we know if we heat up something, the volume of that object is going to increase, like the figure here. If we have a cube, but if we increase the temperature of the cube is going to expand. So we call this length change due to temperature. We have thermal strength. And we define a quantity, coefficient of thermal expansion. This coefficient multiplied by temperature increase will give you the strength due to temperature. This coefficient of thermal expansion, the unit is 1 divided by degree C. So we have, say, different material. Different material has different coefficient of thermal expansion. Okay, next page, please. Now, we have another figure. The figure at the top represents the relation between stress and strain. The y-coordinate represents stress. The x-coordinate represents strain. So if we do a test, young man, I need your help again. Yeah, please. Now everyone, please pay attention to me again. So like we will do some test. Okay, please. So this end fixed, the other end, I apply force 1. Then I calculate the strain, the change, the inner length. Then apply a larger force. I can calculate the new stress and calculate the new strain. Then I keep increase. Eventually, what will happen to his hand? Eventually, I'm going to break, tear apart. So, okay, thank you. So in this figure, if we have a material, say aluminum, the metal, we do the test, we increase the force and measure the deformation. And we calculate the stress and the strain. We can get the curve for this stress with strain relation. Then initially, the relation between the stress and strain is a straight line initially. But later, it will bend. Then eventually, it will break. So for the stress strain in the linear relation, if their relation is a line, like initially, the relation between stress and strain is a linear line. So we call this region elastic region. But if now the linear relation we lost, if we lost the linear relation, we can call yielding occur. Then they are no longer in the elastic region. Okay? So in the elastic region, the slope of the straight line, the slope, we can calculate the slope by delta epsilon divided by delta sigma. We call this slope, the quantity, the slope, Young's modulus of the material. Do you get it? Okay. Young's modulus. Please pay attention to the PPT.
Yeah, just hold on.
Yes. Okay. So you see the Young's modulus equal to delta sigma divided by delta epsilon. Okay, so that's what you can take away from this PPT, the definition of Young's modulus. Each material has its value of Young's modulus. Like each plant, if you do the test for each plant, you can get the Young's modulus for each plant. Okay, very good. Next page, please. 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 Next. 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 Okay, now the bending. Because remember the first PPT, I asked you if you hang on a horizontal bar, if the bar is going to break, where does the point, the point for the bar to break? Most of you said it's at the middle. So I said, okay, we have a problem. Bending problem. If we have a bar, then if we bend the bar, like we have a bar, okay, everyone here, I'm a magician. I'm going to make something magic happen. I bend the bar. This is bending. So I apply a force to this point. But at the same time, force divided by the length is the torque or moment I apply to this point. So in this case, if this tube is going to break, which is the point, the breakage point? Horticulture major. Yes. So we call this bending. And the bending stress, the maximum bending stress is at this point. So now if I ask you, if I hang on a straight bar, like you need your help. Could you please fix this point? So if I hang on this bar, now which point is going to break?
That.
Yeah, so no middle. It's near the root of the support. Because if we apply bending, the stress, the maximum stress is going to happen near the root of the support. Okay, thank you. Next page, please. Okay, next page. Okay, bending stress. We use the moment times the thickness divided by the second moment of inertia. But this is too complicated for you. Next page, please. Now is our study work time. We have a spatula. So we use it in the kitchen for cooking, to fry, for vegetable, potato. So when we use the spatula to cook, we hold the end, the bar, the holding, and the tip of the spatula is going to strike on the pot or on the pan. Then we are going to create stress inside this spatula. Now we can calculate if we apply a force at the end of the spatula and the other end strike on the pan, then what's the stress distribution inside this spatula? Then we are interested in, if we are an engineer, we want to design a spatula, we need to calculate the stress distribution to make sure under normal operation condition, the maximum stress is lower than the maximum stress the spatula can support. Otherwise, the spatula is going to break. So this is one job of a mechanical engineer. So if you are a mechanical engineer, maybe your work is to design the spatula, and your boss might ask you to use the SolidWorks to calculate the maximum stress inside the spatula to determine if your design is good or bad. Do you follow me? Very good. Okay, now we have the model, because I'm not going to ask you to use SolidWorks to draw this spatula. It's too much. So you can download the SolidWorks model from the iLearning. I post the link to download this spatula on iLearning. So you can download this file. So now let's TA, please. Next page. So you can download a lot of CAD model from this website for your final project. Because maybe only 2 weeks from our final project report. So you can either draw your own model or you can go there to download the SolidWorks model for your final project. Next page, please. Okay, so for the material, we are going to select stainless steel for the material properties. And the yield strength, 172 megapascal, is the maximum stress. The maximum stress. Hello? What the yield strength is the maximum stress the material can support. If the stress, maximum stress is larger than the yield strength of the material, your material might break. Okay, so tell me what's the definition of yield strength? Again, I just kind of repeat what I said. The maximum stress the material can experience. Yes. Okay, so in the material property definition, we need to define Young's modulus, which is elastic modulus. And the Poisson ratio. Remember, I said, young man, I need your help. Could you be my model? Yeah, please. Yeah, again. I stretch his hand. Stand still. No, don't move. If I extend his hand, his length here is going to expand, but the width is going to be shorter. So the strain in the length direction, we have the strain in the width direction. If I stretch his hand, I calculate the strain in the width direction divided by the strain in the length direction. This is Poisson's ratio. It's also a material property. Thank you. So that's why we need to define Poisson ratio here. Also, we can define mass density. and the yield strength. You can get all these numbers from any mechanical engineer design handbook or Google. If you Google aluminum material property, it will give you all the information you need for your final project if you need to define your material properties. Okay, next page, please. Okay, so suppose if we use the spatula to hit the pan, so we assume the end of the spatula is the fixed point, fixed to the pan. Next, and we apply the load to the end of the spatula, say force 1 Newton. Okay, next page, please. Then we create a mesh. Next page. Okay, we check the quality of the mesh. We prefer the, say, maximum aspect ratio, not too large. Usually we prefer a mesh with aspect ratio close to 1. That's the perfect case. But usually it's not easy because they will need a lot of elements. And more elements, more computational time, because we need to solve a very huge linear equation, a matrix like Kx equal to F, the linear equation. You have more elements, the rank of the equation, the matrix is going to increase. If you have a large number of the equations to solve, it's going to take more time to do that. Okay. So anyway, there's a trade-off between number of elements and your solution accuracy and also computational time. So you can play with them to get the best condition. Because more elements, more accurate result, but more computational time. So, and the aspect ratio close to 1, we may need more elements, then more computational time, more accurate result. But if you increase the aspect ratio, less elements, less computational time, less accurate result. Okay, so that's the game to play. Next page, please. So next, after you run your simulation, you can plot the stress distribution. Then you will find out the maximum stress. Von Mises, you can just think it as a effective stress measure. So von Mises stress is the effective stress. Here is near 90 megapascal. But the yield strength of the stainless steel, typical yield strength is 172 megapascal. So the maximum stress, 90 megapascal, is less than the yield strength of the stainless steel material. Then your design under this operational condition is safe. Okay, so lady, why did I say this design is okay? Okay, could you help me to answer this question?
Because it's because the force they apply on it is lower than the yield. like it says the maximum stress is lower than the yield stress.
Okay, great. This is a very educated, high quality answer. So you made my day a happy day. Really. Next page, please. Okay, we can also calculate the deformation of the model. Next page, please. Now, because if we use our spatula for cooking, you know the temperature is going to increase. It's not room temperature. So we can do this thermal simulation. Next page. So again, material property. Now we need to specify specific heat. Okay, I would tell this gentleman. Heat input equal to specific heat times temperature increase. So if we input the heat, you look disappointed. Can you open your eyes like sprinkle?
Okay, I try.
Yeah. Like in a cartoon, the animation. So those characters, their eyes would like shining stars. Okay? Heat input equal to specific heat times temperature increase. So if we input some amount of heat into your model, then you can calculate temperature increase by heat input divided by specific heat of the material. Now, after that, you can get your temperature increase of your model. Very good. Then, coefficient of thermal expansion, because if we put heat to the model, if it's going to extend due to the thermal expansion. So we use coefficient of thermal expansion. We need it to calculate the deformation of your model. Is that right? Okay. So remember, coefficient of thermal expansion. Please, yeah, stop. Just yes. So coefficient of thermal expansion times temperature increase equal to the thermal strain. So remember how we play the game. Heat input divided by specific heat, we get temperature increase. After that, we can use coefficient of thermal expansion, alpha times temperature increase, to get thermal strain. If you know the thermal strain, you know the deformation of your spatula. Is that right? So do you follow this argument? Heat input divided by specific heat gives you temperature increase. Then coefficient of thermal expansion times heat temperature increase equal to the thermal strain. If you know the thermal strain, you know the deformation due to temperature increase. Because strain is the change in length divided by original length. So if you know the original length, you know the thermal strain, you can calculate the change in the length of your model. Okay. Do you agree with me? This flow, this logic thinking, the flow of this thinking.
Yes.
Okay, next page, please. Now we give temperature input. We need to calculate the temperature. But we know when we cooking, you know the temperature of your hot plate or the oven temperature, like the surface of the oven. So we know the temperature, say 200 degrees C. Next page, please. Then we know this, because we have air around the spatula. So we need to calculate the heat exchange between your spatula and the air. So we need to define the surface area. The surface area of the spatula, because the surface area, the surfaces is going to contact with the air. So there's a heat exchange between the surrounding air to your model. So to model this heat exchange between the air and the model, we need to define the surface area of the spatula. Do you agree? Yes. Okay, next page, please. So the heat exchange between air and the spatula, we call this convection heat exchange. Okay, next page, please. Then we create the mesh. Okay, next. We check the mesh. Next. Then we run the simulation. You will see the temperature distribution. Because between the oven, the hot plate, and the spatula, they contact with each other. We have heat conduction. The heat transfer from the hot plate to the spatula. And between air and the spatula, we have heat convection, because air can flow. So this flow of air helps to dissipate the heat from the spatula. So the temperature distribution near the bottom is 200 degrees C, but near the hand, the holding position is room temperature 25 degrees C. So that's kind of how when you cook, the tip of the spatula is under high temperature, but the position for you to put your hand on the spatula is low temperature. Okay, so it is exciting. It is exciting. Okay, your sprinkling eyes, please. Okay, good. Next page, please. Okay, we have because after we can calculate the deformation of under this thermal load, the temperature. Due to temperature distribution, we can get the deformation. So we click on new study, static, because we want to know. So previous simulation, we get the temperature distribution. Now we want to know the deformation due to this temperature distribution. Next page. Okay, next page. Next page. Next. 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 Okay, you run the simulation. Because this new temperature distribution, the temperature is going to change the deformation of the spatula. So due to this operation, due to the temperature increase, the maximum stress is 70 megapascal, less than the yield strength of the spatula. So if we consider the temperature, the stress due to temperature, the maximum stress due to temperature is also less than the yield strength. So good. This is good for us. So either we play with the spatula to cook. The maximum strength maximum stress under this, you put the force on the spatula, is safe. And the other scenario, we consider the temperature increase. Then the maximum stress is also less than the yield strength. So under these two criteria, we think our design is good. Do you know why we have some gap? We create some holes, some gaps in the spatula. Yes. Do you know why?
No.
Okay, young man, I need your help. Come here, please. Okay, everyone, please. Like, I wear my jacket. The jacket covers almost all my skin. And this young man, he wears a shirt, so he exposed his skin. A lot of surface area is exposed to the air. So my warm jacket is going to keep my body warm because I have less surface area contact with the cold air. But he exposed his surface area to the air. Then he's going to feel cooler because the larger surface area. Okay, thank you. Okay, for this case, we created some holes inside the spatula. So you are going to increase the contact surface area between air and the spatula. So it's easier for the spatula to dissipate the heat. Because larger surface area, you have larger contact surface with the air. Then it's easier if my temperature is very high. Then the heat inside my body is easier to get out if you have large surface area contact with the air. Okay, one of the reasons is we create some holes inside the material. We increase the surface area of the spatula. Easier for the spatula to dissipate heat. Okay? Do you agree with me? No? So,
Yes.
okay, thank you. Next page, please. Okay, the thermal, due to temperature increase, we can calculate the deformation due to temperature increase. Next page, please. Okay, next. Okay, we are done. So now, let's go to iLearning. Go to our course website, iLearning. Okay. Go up. No, not that. That's just the announcement for the final project. Lecture 8 is a PPT. Please go to not the PPT, the material 上课教材. Okay. Under 上课教材 material, you can download Lab A model file. Can you download the file? Yes, please. Yeah, this is a file for you. You can import this file. So please go to SolidWorks to import this file. 博全 TA, please demonstrate. Yes. In iLearning, we have the video, the tutorial video. You can follow the tutorial video. Okay, now I guess in order to save the time, let's turn to the operation mode for every student. So you could go to iLearning and download the video and follow the instruction of the video. So our two TA will go around to help you.